today's lecture we are going to discuss combinational circuit design using MSI blocks. In the last lecture we talked about how to specify a Boolean function and then also reduce it using Carnot maps before and then realize it using logic gates. Today we are going to talk about realizing similar functions using MSI blocks. But before we do that, there is one point that we did not discuss last time, so we will start talking about the incompletely specified functions. Very often we come across functions where the output is not required to be specified for all input combinations. We will see under what conditions this occurs. We can use the same Carnot map procedure for minimizing that. So here we have a function which consists of two parts. I have a set of minterms for which the output is specified to be 1, and then I have a set of minterms for which I do not care what the output is going to be. So I am writing such a function as summation of the minterms where output is specified to be 1 plus summation of minterms for which the output is don't care. I draw the Carnot map for this in an exactly similar manner as before, except that for those minterms, so for example here this 10 corresponds to 1010, 1010 is over here. So for those minterms I should specify, there are yeah, so there is, I think there is a small mistake over here. So this should have been 1, 1, 8 and 9, and this should have been don't care. So this corresponds to 12, 13, 15, 14, and this corresponds to 10 and 11. So I should have my function to be written in this manner. So I can now minimize it. When I want to minimize using Carnot map, what I will do is this don't care minterms, it's up to me whether you include them in my output or not. I will include them if I can minimize the number of literals. So in this manner, so I can form one term like this. So this is a product term in which basically A and B both are eliminated. So my output corresponds to C D bar. Now let's consider this one. So in this case I will have one output which corresponds to this. So this corresponds to, I am going to eliminate B. I am also okay. Yes. So this is going to eliminate 3 variables because it has 8 of them present, 1, 2, 3, 4. So I am going to eliminate B as well as I am going to eliminate C and D because all the columns are present. So this will correspond to plus A because only A is available. A is to be taken care of. Then I can have one term which corresponds to this, which would be, I will be eliminating here D, so it is C prime, and I will be eliminating, so BC prime. A will be eliminated, and now I still have to have this, so I can have combine it in this manner, and this will be D will be eliminated, so that will be C, and also A will be eliminated, so it is B prime D, sorry, B prime C. So that corresponds to the output function. In this case it so happened that all the don't cares were converted into 1, but that is not something which has to happen each time. We can have some don't cares which may remain because I don't really care what the output is going to be for these minterms. So some of them may remain 0 and some of them may remain 1. But of course once I have minimized it and I return the function in this form, it is very clear that the output is either 0 or 1 for these minterms. It is no longer don't care. So depending upon whether that particular minterm has been included in the expression that you have written or not included in the expression you have written, the output would correspond to. So the don't cares do play a role in minimizing the number of literals in the output and thus simplifying the output itself, the expression, the output expression. How does this don't cares occur? Okay, why incompletely specified functions at all? So there are two different situations under which these don't cares can come, and of course as far as minimization is concerned, we do not treat them separately. One is outputs actually do not matter for certain subset of inputs. That's one type of a situation. And second is a subset of inputs do not occur or cannot occur. Okay, so both of them actually correspond to the don't care situation. So if there are a set of inputs, for example, what I showed to you now, this particular function that I wrote, it essentially corresponds to, if you look at these min terms, it corresponds to when you want to convert a BCD number into a 7 segment display. So we have 7 segments here, and if you consider this particular and I want to, so what I have is I need a circuit which takes a BCD input, so it's a 4-bit input, binary coded decimal, and it's a 7-bit output. The 7 bits correspond to the 7 segments that you have over here. If you consider this particular segment, so this segment corresponds to, this is going to be 1 for which cases? For 2, for 3, for 4, for 5, 6, 8 and 9. And it will be don't care for 10 to 15, 10, 11, 12, 13, 14, 15. Basically because in a binary coded decimal, the only input combinations that are going to occur are 0 to 9. Because it's a decimal input, so you are not going to get the other combinations from 10 to 15. So, and that was this particular function that we showed and minimized. So, of course, there are also other cases where we really do not care what the output is for a certain set of inputs. So, both situations can occur. Now, let's get on with the design of combinational circuits using MSI blocks. So, the blocks that we will be considering today, of course, decoders, encoders, multiplexers, ROMs and PLAs. So, we will not today do any designs using encoders, we will do it maybe some other time, but today we will consider the decoders, multiplexers, ROMs and PLAs. They all have increasing amount of complexity in terms of what you can, this type of circuits that you can design using them, and also there are certain situations under which one could be preferred over the other. When we talk of MSI blocks, we talk of medium scale integration blocks which are medium scale integration, and there are other blocks also which are arithmetic MSI blocks like adders, subtractors, ALUs, comparators. Later we will also talk of design of these blocks and also design using these blocks, but today's lecture will primarily concern realizing combinational logic using decoders, multiplexers, ROMs and PLAs. So let's first start with the decoders. So typically a symbol for a decoder is shown in this manner, and what we call them as n to 2 raised power n decoder. That means there are n inputs. So in this case, if you say that there are 2 inputs over here, so I can say that the 2 inputs are A and B, and I will typically also can number them as 1 and 0. This is just to give an order, because as we look at the output also we number them as 0, 1, 2, 3. And this decoder corresponds to nothing but, the 0 output is nothing but A prime B prime. This is nothing but A prime B, AB prime and AB. So essentially it decodes each of the 4 min terms that are possible for a 2 input function. So we have the 4 outputs corresponding to the 4 min terms. So similarly, if you have 3 inputs, you can have 8 outputs, 4 inputs, 16 outputs and so on, and that is a full decoding n to 2 raised power n. Sometimes we also use partial decoding. For example, if this 4 inputs correspond to a BCD input, we may be only interested in decoding the 10 outputs. So it will be a 4 to 10 decoder, just each of the output lines will show which correspond to, the input corresponds to which digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a partial decoding, but full decoding will mean that n inputs and 2 raised power n outputs. So how will the circuit itself is a fairly simple circuit. So in this case, you can draw them as basically a set of AND gates, and you could have two lines that are running which corresponds to A and B, and the inputs to them will vary depending on what you are decoding. So for example, this will be, so this is A and B, and this will be and so one can design a decoder itself in this manner, fairly straightforward. And if you are talking of 3 inputs, then you have 3 input AND gates and so on and so forth. So this type of a decoder, we also say that the outputs are active high. That means when the input, particular input combination that you are looking for, you get that particular input combination, the output is 1. The outputs are mutually exclusive in the sense that only one of the outputs is going to be 1, because at any one given time you can have only one of the input combinations corresponding to the only one minterm that can be present. So we also talk in terms of decoders which have active low output. That means the selected in combination will have an output 0 and rest of them to be 1. Of course, such a decoder can be designed by simply using NAND gates instead of. So whichever you are decoded, so you can have an AND over here, and so you will basically will have only 1 0 and rest of them 1. So many times actually active low decoders are used, though for the present discussion we will use the active high decoders, but later when we talk about designing with memories and so on, where the decoders are used extensively, many times one uses active low decoders, where the output is active low. How can I implement a function using this? It's a fairly straightforward to implement functions using decoders, and I have an example of a function over here. So this is a decoder which is a 3 to 8 decoder, and I have 3 inputs A, B and C, and I should actually clearly label this. Whenever I talk of a labeled decoder, I should label both the inputs and outputs. The order is important, because when I am saying A, B, C and this particular function is written in terms of these minterms, when I say 4, 4 corresponds to 1 0 0, A being 1, B being 0 and C being 0, because that particular order is important. And if I want to implement a function using decoder, I primarily, because I am getting all the minterms here, the 0 to 7, 8 minterms that are possible are already decoded and available. What I really need to do is just to OR them. So I take this particular inputs 0, 3, sorry, that's 2, 3, 4, 6 and 7. I take and put an OR gate, and this particular thing correspond to my function y. Because if any of the input combinations are present, which is 0, 3, 4, 6 or 7, one of these will be 1, and I am just ORing them and generating my output. So which is nothing but, so the minterms are implemented by the decoder, and the sum of minterms, that the summation function is implemented by the OR gate. So it's a fairly straightforward method of implementing functions. So if you using a decoder and an OR gate. So now let's talk about the second MSI block that's of interest to us, and which actually is very efficient in implementing many functions, which are called multiplexers. So in case of multiplexers, I have two sets of inputs. One is the data input, so I can call this data input to be x0, x1, x2, x3. Of course, I have an output y, and I also have select input s1, s0. So if you look at a multiplexer, so we typically specify the multiplexer, saying that it's a 2 raised power n is to 1 multiplexer. What we mean is there are 2 raised power n inputs for the data, and there are also n select lines which are required to select one of the inputs to the output. So in this case, it's a 4 is to 1 multiplexer with 4 data inputs and 2 select inputs. So if we talk of a 8 is to 1, there will be 8 data inputs and 3 select inputs and so on, and output itself is 1. So if you look at the output function of such a multiplexer, let's say we talk of a 4:1 multiplexer, the output is nothing but x0, s0 complement s1 complement, x1 plus x s0 s1 complement plus x2 s0 complement s1 plus x3 s0 s1. So now two things are happening over here. If you remember the decoder situation, so I am actually decoding these 4 minterms in a multiplexer, and these minterms are being decoded for the 2 select inputs, not for the data, and I am gating it with the appropriate. So what happens is, when I do this, depending upon what the select input is, so if S0 S1 corresponds to, let's say, 1 0, so that corresponds to x2. So x2 is going to be the output y, because rest of them is going to be, so in this case I can again number the inputs to be. So depending upon what S1 S0 combination corresponds to, that particular data will be traversed to the output. And that's what this particular equation signifies, because only one of these 4 is going to be 1, and output corresponds to, if you replace others by 0, so they get eliminated, and so like S0 S1 is 1 1, then x3 y will correspond to x3, and that's what. And so this thing can be again very simply be implemented in a very similar fashion as before. Only thing is, I have an extra data input, so that's all. Otherwise the so I will have one x0 to be data input, similarly x1 to be data input, and so on, and I will take this output now and also OR them. I am not drawing the complete figure, you can complete it, and this is what is the implementation itself is going to look like. Okay, so this is, let us say, S1, this is S0. So okay. From this diagram itself, it becomes clear that it is a complete implementation of the function. You don't really require anything much to implement a function, because both the AND as well as the OR operation is taking place. If you are talking of the decoder, remember we were only performing the AND, and then we had to provide an external OR. So let's see how can we implement, using multiplexers, how can we implement functions. So we have this function being implemented using a multiplexer. So now what we have over here is the same function as we considered before. So I would now have the 3 select lines, and these 3 select lines have to be unified to S2 will be A, S1 will be B, and S0 will be C. The same order as they are for the minterms. And again, of course, I am not writing over here is 0 to 7. So now wherever the minterm is supposed to be 1, like 0 1 3 5 6. So 0 1, so this is, let me just write the numbers for this, 0 1 2 3 5 6. So those of the inputs can be tied to 1, and those in minterms which are absent over here, namely 2 4 and 7, 2 4 and 7, they can all be connected and connected to the ground. Of course, this corresponds to 1, and this corresponds to VCC, which is 1, and this corresponds to ground, which is 0. That's the symbol we typically use. So now what we have over here is, if this S2 S1 S0 corresponds to one of these combinations, let's say it corresponds to 5, then it is going to select this particular input to the output. That's what was the multiplexer function that we have seen. and this particular input is nothing but 1. So output is going to be 1 corresponding to, if I get S2, S1, S0 to be 5, that is 1 0 1 combination will select this one, and I will get my output to be 1, and this is my y, and that is what I am expected to get from this particular function also. So this is a fairly simple implementation of a function using multiplexers. We will see something which is even actually cheaper than this, because this particular implementation requires, let us say if we are talking of a 3 input function like we have over here, we require a 8:1 multiplexer. If you are talking of a 4 input function, we require a 16:1 multiplexer, because primarily all these inputs correspond to each of the minterms that are possible for implementing the function. Let us take an alternative implementation which actually is more economical. In this case, I am trying to implement a 8:1 function using a 4:1 multiplexer. So I have a multiplexer which has only 2 select lines, S1 and S0, and I want to use it to implement a 4:1 3 variable function. Typically this multiplexer directly can implement only a 2 variable function by connecting this A and B to the select inputs and taking the proper minterm. What I can do is I can analyze this function around any one of the 3 variables. In this case I have chosen A. It is not necessary that you have to choose A, you can also choose B or C. So if I choose A and split this function into 2 parts, I consider the minterms 0, 1, 2 and 3. So these are the minterms with B and C. So I am going to connect B and C over here. So S1 is to be unified with B and S0 is going to be unified with C. So these are the 4 combinations for B and C. So now let me look at under the condition what happens with A is 0 and A is 1. When A is 0 and B and C are 0, so I am talking of the minterm 0. So minterm 0 is 1. And when A is 1 and B and C are 0, I am talking of the minterm 4. 4 is absent. So that means for the output function has to be 0. Now again I consider with A to be 0 and B and C, BC to be, that is 0, 1. So that is 1 corresponds to 0, 1. So this is 1 and 5. Both 1 and 5, the function output is 1. So now A to be 0 and BC corresponds to 2, that is 1, 0. So this corresponds to 2 and 6. 2 is 0 and 6 it is 1. A0, B and C to be 1, 1. So this corresponds to 3 and 7. So what I am doing is I am splitting this function around the variable A. So this corresponds to minterm 0, this corresponds to minterm 4, this corresponds to minterm 1, 5, 2, 6, 3, 7. And I written down the proper 1 or 0 looking at what this minterm is going to be. If I have a don't care incompletely specified function, I can write don't care also here. An important thing to look at it is if you look at these 2 rows, or let us say you look at any column, what does this column correspond to? This particular column corresponds to the fact that when S1 is 0 and S0 is 0, I am going to select this line to the output. That is what this column corresponds to. Irrespective of what A value is going to be, I am going to select this line to the output. So now if I connect A complement, so when A is 0, this output I want is to be 1. When A is 1, I want the output to be 0. So I can connect A complement to this. Now let us consider the next case. When B is 0 and C is 1, that is B is 0 and C is 1, I am going to connect this particular input to the output. And in this case, in both cases, I want output to be 1, so I can connect 1 to this. Similarly, when B is 1 and C is 0, that means 1 and 0, I am going to connect this particular input to the output, and in this case when A is 0 I want, so I can connect A over here. And in the last case again, when it is both are 1 1, I am going to connect this and I can connect A prime. The interesting thing to notice is, because we are talking of splitting around one variable and we are talking of two entries, we have only 4 possibilities over here. Both can be 0 0, both can be 1 1, or it can be 1 0 or 0 1. So there are no other possibilities. So if you look at any of these columns, you can have 0 0, 1 1, 0 1 or 1 0. And these 4 corresponds to 0 1 A complement. So what I can do is, for implementing a function in this particular manner, the only thing that I need to do is, I can take a multiplexer, let's say, and I have 2 select lines BC. I have VCC and ground, very similar to before, and now apart from that I need only 2 more columns. One column is A, so this is A and this is A complement. And I can implement any 3 variable function and for implementing any 3 variable function, what I really need to do is program this part. Meaning I had to make a proper connection. I had to select for each of these cases, I had to select one of these, either A complement 1 or 0, A complement 1 or 0. So for each of the inputs, if I select one of these 4, I can implement any 3 variable function using a 4:1 multiplexer. So the implication is, so instead of using a 8:1 multiplexer, I can use a 4:1 multiplexer. Of course, something additional I have used one inverter. So one inverter plus, so what it implies is, let's say you have to implement a 4 variable function. So either you can use a 16:1 mux, or you can use one inverter plus 8:1 mux. Because this is irrespective of what you do, you can split around, choose one variable, split it around that, and then use that variable to feed the inputs, and the inputs are going to be 0 1 A complement, whichever is the variable, and rest of the variables you can use to generate your select lines, to select the proper inputs. So just to recap, the reason it works is when it is 1 0, so this line is selected and I am controlling here depending upon A whether it is going to be 0 or 1 depending on what I want for my function. So that's the important thing, that so I can use, so similarly for any 2n any n variable function, I don't have to use a 2n=1 mux, but I can use a 2n-1=1 mux and just add one inverter to it. Interestingly, this type of a decomposition is not possible not just with one variable. I can use this to implement a 4 variable function, but then what happens is these inputs themselves can be a function of the other 2 variables which are left out. So if I have A, B, C, D, I can use C and D, and then these inputs can be a function of A and B. We will talk about this type of a decomposition later in the course, because this is fundamental behind implementing a whole series of logic where you can implement just using multiplexers. But here we have seen the implementation of functions with one less select input than the number of variables. Okay, next we go to talk about implementation of logic using read-only memories. When we talk of a memory unit, we talk in terms of 2 parameters. We say a certain memory is 2n into m. So we can say where 2n corresponds to the number of locations, it also corresponds to n address lines. So I have address lines A0, A1, A2, A3. So there are 4 address lines. So I have 16 locations that I can address using these 4 address lines. And I have one output. So this is basically because there is only one output. So this particular ROM corresponds to 16 by 1 ROM. So if I have multiple outputs, I can have this ROM corresponding to. So what this ROM lets you do is, this is a fairly simple way to implement functions using ROMs. This is a direct implementation of the function. I will show you how this direct implementation works. The other great advantage about ROMs is it's extremely flexible, as you get ROMs which can be reprogrammed, and reprogramming can implement a completely different function. Later on we will see the use of such a thing in implementing control units of various designs. Because if I need to change my control, the only thing I need to change is the ROM, contents of the ROM. The rest of the design can remain the same. How can I implement directly a function? Remember, what is happening over here? How is this ROM, a 4 variable ROM getting implemented? So you have 4 address lines. So you can assume that these 4 address lines are getting decoded. This is all inside the ROM. And I am getting my 16 outputs out of the decoder. And I have these locations. And what I am having is, I can take this output. So this is a functional equivalent. The ROM is actually not implemented with this type of a logic, but what I am showing you is functional equivalence. So this is my ROM. And what are these cells? These are the cells which I can program to be 0 or 1. So if I want to implement a function where this particular minterm, so I can implement a function which has 4 variable function. If this particular minterm that is corresponding to 0 is, let us say, 1, then I can make it 1. If minterm corresponding to 1 is 0, I can make it 0. The minterm corresponding to 15 is 1, I can make it 1, and so on. I will have, of course, other minterms in between. So what happens is, this decoder, this particular output is getting ANDed with this, and then I am ORing. So depending upon what the address is, this particular line is going to get selected. Only one line is going to get selected, because the decoder output, you know that only one of the outputs can be 1, and that particular cell is going to be appear over here if it is 0 or 1, and then that's going to come. Rest of them are going to be 0. So if your address is going 1, that is 0 1 0 0, sorry, 0 0 0 1, so then this particular output is going to be active, and this cell is going to get selected. Of course this cell is also 0, so I am only going to get an output of 0. So a ROM contains all this logic internally. So what you don't have to need to build in anything. So you basically only have to give the, instead of the address, you give the variables which you want to implement as a function. Choose the minterms. So wherever the minterms are present, make them 1, and minterms which are absent, make them 0, and directly you will get the output corresponding to this. So this is for implementing a 4 variable function. You can use a 16:1 ROM. You can also use a ROM which has, let us say, I have a ROM which is 16:4. That means I don't have just one cell, I have 4 such cells. And these 4 cells have their own independent AND gates and an OR gate. So I can implement any 4 functions of the same 4 variables, because my address lines are common. The functions can be completely independent of each other. There is no relationship between one function and another, because depending on what I program over here, because correspondingly I have 64 cells. These 16 cells correspond to one function, the next 16 cells will correspond to another function, and so on. But because the address lines are shared, these 4 functions that I can implement should be the functions of the same 4 variables. As long as they are of the function of the same 4 variables, I can implement any 4 functions. So the ROMs gives you an extreme flexibility in terms of implementing any function that you need, and also you can change the function by just changing the ROM or reprogramming the ROM with different values. Now we go to what are called programmable logic arrays, PLAs, which are used extensively for implementing combinational logic. PLAs more or less correspond to the way you will talk of implementing a, if you consider a Boolean function, it's either it can be sum of product or product of sum. So here we are talking of sum of product. So you have 2 things over here. You have to perform an ANDing, and then you have to perform an ORing. ANDing to extract, of course in case of decoders and ROMs you are extracting the minterms. But it's not necessary that if you consider a sum of product function, it's not necessary that you have to implement always the minterms. You can also implement what are called product terms. Product terms could have some of the literals be absent. It's not necessary that all literals have to be present in either in true or complement forms. So this is a sort of an internal design of the PLA. So PLA itself will come with a boundary like this. It consists of 2 things. It consists of an AND plane and it consists of an OR plane. So you have some variables. Okay, something that is missing here I will draw. A PLA is specified with 3 parameters, N, K and M. N is the number of inputs. Okay, this should have been small. N is the number of inputs. So in this case I am talking of 3 inputs, A, B and C. So N is 3 for this particular PLA. K is the number of product terms that you can implement. Product terms here correspond to the number of rows. So in this case 1, 2, 3, 4, 5, 6. There are 6 rows that are available over here, and so I can have 6 product terms. M is the number of outputs. So in this case the number of outputs is 4, y0, y1, y2, y3. Of course I could have done x0, x1, x2 also as inputs, doesn't matter. So that is corresponds to the 4 outputs. So these 4 columns correspond to the 4 outputs. We will see that how we can implement functions using this, but what PLAs provide for is, it provides for, if I want to implement a function, we will see an example implementing logic using PLAs, direct implementation of sum of products. I can directly implement the sum of products on the PLA by implementing the product terms in the AND plane and implementing the sum in the OR plane. So let us see an example of an implementation, and then we will come back to some properties of these PLAs. So here I have 2 outputs that I want to implement, y1 and y2. y1 consists of 2 product terms, AB, B prime, C prime, D prime, and y2 consists of AB plus BC prime plus CD prime, C prime, D prime. So in this case again, so this particular column corresponds to A, this corresponds to A complement, B, B complement, C, C complement, D, D complement. I choose each of the product terms, and basically what I have to do is, of course the programming a PLA essentially means you are going to fuse. What you are going to do is make some of these connections that are, so in this case I want to have AB as to be one product term, so I will have A, B. So this particular product term now corresponds to AB. I need a product term B prime, C prime, D prime. So I need a product term B prime, C prime, D prime. So this will correspond to B prime, C prime, D prime. If I go over here, AB is already present, so I don't have to do, so BC prime I need, so B C prime, and C prime D prime, C prime D prime. So I have BC prime and C prime D prime. So I had 4 distinct product terms for implementing these two functions. Of course there are 5 product terms, 1, 2, 3, 4, 5, but one of them was common, so I need to have only one implementation for that. And now in terms of the OR, Y1 is product term 1 and 2, and Y2 is product term 1, 3 and 4. So Y1, so this is an OR plane. So what it is going to do is it is going to OR AB plus B prime, C prime, D prime, and this is going to OR AB plus BC prime plus C prime, D prime. And so these two functions I can implement now using a PLA. Now the PLA, the size of the PLA is 4 inputs, 4 into 4 into 2, because 4 inputs, 4 product terms and 2 outputs. So the size of this PLA is 4 cross 4 cross. PLAs give you certain advantage and certain disadvantage. Of course, a major advantage in case of PLA is that the logic is much less if you compare it with the corresponding ROM. First of all, full decoding is not done over here. I don't need to, for example, if I try to implement it using either decoders or multiplexers or using ROMs, what would I have done? I would have to implement this AB as the sum of 4 minterms, AB C prime D prime, AB C prime D, AB C D prime and AB C D, because there will be 4 locations which you have to program as 1 to just get this output function AB, and the decoders that correspond to that obviously are going to be present within the ROM. Of course, it is a packaged device, you don't see those decoders inside, but if you want to design your own chip, you are actually going to have invest the cost of having those decoders. Here I do the decoding, only partial decoding. If I need AB, I can just get AB over here, which I don't have to actually talk in terms of the minterms. And typically what happens is a large number of functions can be implemented using a few product terms. So this is the experience. You don't really need all the minterms, decoding of all the minterms. On the other hand, there is a restriction that you cannot implement all 4 variable functions. You cannot use this to implement all 2 output 4 input functions. There may be functions which will actually require more than 4 product terms. If you require more than 4 product terms, this particular PLA is not going to be so adequate to implement such functions. So that is a restriction, but by and large this is very compact, because basically the area of this device is much smaller than the area of the corresponding ROM, because I don't need to decode all the inputs. I can also easily share. Of course, sharing of the decoders gets done in the ROM also, because the same decoder, but primarily because I don't have to decode. So if you are talking of functions of large number of inputs, 8, 10, 12, ROMs can become very large in size corresponding to, in comparison to the PLAs. So I will try to sum up now what we have discussed today by talking of the various ways. We discussed a number of ways to implement an n variable function. Let us say I am talking of implementing an n variable functions with k minterms in the sum of minterms, the canonical form, the sum of minterms. I can use an n to 2 raised power n decoder, and I also need a k input OR gate to take the OR of all the k minterms that are present to generate my output. So this is one option. Second option is I can use a 2 raised power n is to 1 multiplexer. Because I have n variables, I can use those n variables as the select inputs, and I can use 2 raised power n. The corresponding k minterms which are present, those inputs will be 1 and rest of the inputs will be 0, will be tied to the ground, and I can use this. Alternatively, I can use a 2s power n minus 1 is to 1 multiplexer, but I will need one extra inverter to take one variable. So each of the inputs of such a multiplexer will be selected out of 0, 1, A complement, where A is a variable which has been chosen, which has been not been used for the select input. Rest of the n minus 1 variables will be connected to the select input. So this is another implementation. I can use a 2 raised power n into 1 ROM and program the corresponding k, for the corresponding k min terms, the corresponding locations I can program them to be 1, rest of the locations will be programmed to be 0, and I can use a 2 raised power 1 n into 1 ROM. I can use an n into p into 1 PLA. Okay, now when I am using a PLA, because I can actually combine some of these min terms to reduce the number of literals and also reduce the number of actual product terms that are present. So this p can be less than equal to k. Of course, depends on how these min terms combine, how small the p can be, but I can use this for using a PLA. And so we have discussed about 5 different methods, apart from of course using directly the gates for realizing functions, which are anyway there as an option. This along with that the 6 options. So typically in a design, one chooses one of these depending upon what happens to be the most suitable. From situation to situation, at sometimes one uses a ROM, a PLA or a multiplexer. Of course, this type of multiplexer is definitely preferable to this, but sometimes one also uses a decoder, especially if only partial decoding is being used and there are only fewer number of outputs that are required to be odd, then sometimes one uses a decoder. With this we will conclude this lecture.